Alright, so we're going to look at functions today. We're starting off with just regular functions and then we'll look at composite functions after. So everything you see at the moment is just regular functions for now. So a function is a mathematical machine that transforms an input into a regular defined output, singular output I should say. So if we've got this mathematical machine here called f, it's going to transform whatever input x into 3x plus 2. Now this is familiar to you already because you would have already seen that it can be written in this notation here. It's just you guys are year 12 now, so we give you something slightly different. Now for any given function, it's going to have a domain and a range. Be careful not to get these mixed up, Ron. Domain is its horizontal span, so all the valid horizontal values, and its range is all of the defined vertical values. The range itself is based on the valid values that can come out, based on the valid values you can put in for the domain. So let's have a look at what that means. If we have the mathematical machine f that's going to transform x into 2x plus or 2x minus 3, then this effectively is going to be f of x equals 2x minus 3. Now looking at this, what values of x are we allowed to put into this function f here, Nick? What valid values of x can go in?
Probably anything.
Anything. So the domain for this guy is going to be, any real number. Could probably put in complex numbers as well, but we'll just say any real number now because we're not in complex numbers. Now based on that, what is the range going to be? Any value of x is fine, but if we were to graph this, what values are we going to get out? It's a minus 3 and it's quite steep. What valid values of y are we going to get out of this function given our domain? Are we restricted? Are there any values we won't see? So what values are we going to get out? So what's our range? Any real number. So we'll say that our range is going to be any real number. Is that cool for now? Alright, awesome. Next one. Still in year 11 land. Our function g is the machine that converts x into x squared plus 4. Now looking at this, what will function g turn into? G of x equals
X squared plus 4.
Yeah. X squared plus 4. Now this one's an interesting. What values of x are we allowed to put into this function here? Are there any limitations for what values of x can go in?
No. Yeah, if you put in a negative.
If we put in a negative, will it still give us a singular output?
Oh
Yeah. Are there any restrictions, Isaac?
yeah. I don't think so.
No. So x can be any real number. But think about our range here, and this is where you have to consider what will this function look like if we graphed it? It's x squared plus 4, so it's going to be a smiley face, and it's going to have a y-intercept of plus 4. Are there any values of y that are not included in this function? Anything below 4, inclusive of 4 or exclusive?
Inclusive of 4.
Inclusive of 4. So what we're going to find is that y is simply greater than or equal to 4, and there's our range. Does that seem cool? Alright, so not too challenging from what we've seen so far. The only things I'm going to add to this are the ways in which we can describe this here. So this is perfectly fine notation. Another way to do this is, I believe you can write it as, let's say in the braces, x you're allowed to do that. And similarly, you can do it with the y. You could do, what would it look like? So this one, we did the same. It's going to look like that. And there's one more, I'll do it for this one. I believe it's going to be y is such that it is going to...
What does that line mean between the two x's?
It just means that this is what we're focused on, and these are the conditions. So this is called a pipe.
Okay.
Yeah, you just put the pipe to say this is what we're focused on, and this is its condition. Or you can just do it like that.
Are they interchangeable?
They are, but you'll need to know all the notation.
I do remember this actually.
Yeah.
Do you remember that? Set notation?
Yeah, that was so annoying.
That's alright, you'll get used to it. Seem cool? Okay, remind me again, I'll show you how to graph these on your calculator, which of course you already know how to do, but I'll show you how to put in the domain for it. Okay, let's move on.
Should the domain already be like known in the calculator?
It can, but you can restrict the domain. And the reasons why you'll restrict the domain is for what I'm about to show you. Okay, we're going to do composite functions, but before we go on to that, we'll just review the difference between a function and a relation. Does anyone remember? Oops.
I know that relation is like x squared plus y squared would look like a circle.
Like
A locus, yeah?
Yeah.
Okay, a function has a singular regular output for a singular regular input. In contrast, it's an N there.
Do we do relations at all?
You have to know what they are and know the difference between the two.
That's it.
Yeah.
Okay.
In contrast, a relation may have, oops. Consider A and B. Okay, for A, we're going to go the cubic. We will say f of x, in fact, no, we'll just say y. And I'll explain after. We'll say y is going to be x plus 2, x minus 1, x take 4. And then for the second one, we're going to go, let's say 3 squared equals, keep it simple. Is that cool? All right, so first one, you're going to remember from your polynomials topic. If you're in factorized form, you can know what this will look like roughly, Simply by knowing where the roots are. The roots for this one are minus 2. Say minus 2's, no, we'll say minus 2's here. I will say 1 and it's going to be 4. So this may, I might get this around the wrong way, but it may look something like that. Now, this is in fact a function, and the reason why this is a function is because of a test we can do on it. Does anyone remember what test we do? What is it, Nick?
You draw a vertical line.
Yeah, you do the vertical line test. And if you can draw a vertical line anywhere along here and only ever get one single cut, then this is a function. The vertical line reveals if it's a function. So it's a vertical line test. So if you only ever get one cut, you're a function. Now, in contrast, does anyone remember what this guy will look like?
Probably a circle.
A circle, where will its origin be?
Probably number 0.
Probably at number 0, 0, 0, the origin. And what will its radius be?
3.
3. Now, in contrast, we draw a vertical line. Bang, bang. This fails the vertical line test. Relation, not function. And this is important to think about because what we're eventually going to go into is how we find the opposite function, or the function that undoes any given function. If you're getting multiple values out, you can't really have a function that undoes that one there. Does that make sense? So we're interested in relations, but we can't really do the same things we do to them that we do to functions. Is that all right? All right. Final piece of information. A composite function. This is where we start the year 12 stuff. Is made of multiple functions. Consider we have let's say F is the machinery that transforms X into favorite function, Nick.
Probably x plus 1.
X plus 1. And G, on the other hand, is the machinery that transforms
X cubed plus 3.
You sure? All right. Determine firstly, let's go A, and we'll say f of g of x. Any ideas how we'd interpret this?
You input f of x into the function g of x.
Bingo! You import. Actually, it's the other way around. You
Yeah.
import g of x inside of f of x. So what you do is you see the biggest one, the outside, so the f of x. So you're like, f of x transforms x into x plus 1. So you've got an x there and then a plus 1. So whatever you're putting in the function of f is going to appear in this bracket here.
Hey, could you take a risk question?
Yeah, absolutely. Stella, do you want to have a seat over there? And Stella, we've just got the camera rolling, so just be mindful of what you're saying. Alright, so wherever we have g of x, we're going to put it inside of f, so inside here. So we're going to go x cubed plus 3 plus 1. Then we just expand it out and simplify. Does that seem reasonable? Bingo. Next one. We up the notation slightly. Rather than having f of g of x, we're going to have, I call it fog. I don't know if we're supposed to call it that. But we have that. Have we seen this before?
Yeah.
Yeah. How do we translate this, please, Brad?
The same way we've done it.
Bingo, the same way we've done it before. It's just a more concise way of writing the above. And then what you can do is say using A, because we don't like having to repeat ourselves in spec, because we've got so much to write anyway.
Is that actually an O, or is it just?
Nah, it's just a dot, an open dot.
What does it mean?
It means that f of g of x. That's how I interpret it. I call it fog. I don't know if you're supposed to call it that.
That's what this diploma called it.
Okay, nice. What did you have Clemo for?
This.
Okay. Fair enough.
This is methods B.
Nah, this is methods B.
No, we definitely.
Once we did this in the
Okay, nice. Alright, and final one. Golf. Do we know this already, or do we need to do something else?
Yeah, we don't know this.
We do not know this. It looks similar to what we've already done. So much so that I started writing the wrong thing. Like so. Don't know this, so we have to redefine it. So it's going to be the f of x inside of the cubed. So we've got to expand that. Do we remember our binomial expansion?
1331.
1331. X cubed plus 3x squared plus 3x plus 1 plus 3. So there's your seem cool?
Yeah. Why is everything so different when we do composite functions?
We just need to know more notation because sometimes it's quicker to express ideas using that notation there. Like this looks cleaner than that, obviously.
And the arrow,
Where's the arrow?
like.
Oh, this.
Yeah. That.
I don't know why they do that. It looks like a programming language, doesn't it?
Looks like 6.
I think they do it so anyone looking at what you've done won't actually understand what you've done, so you look smarter in their eyes.
It's like obnoxious. Like it looks so smart.